Okay, let's begin, everyone. This is the lecture summary, daily lecture summary that I advise everyone to look at every day. And so I have posted the extra meeting 15, the continuation of the review for the single degrees of freedom system. So please do watch the video, read the lecture notes as part of the course. Since you have this material in differential equation, this is a review. Now, to continue with improving or developing good communication of ideas and facilitation of learning, I have already mentioned the weekly schedule, and right here we are focusing on this part here. The weekly schedule, the list of topics and how you search for topic and the corresponding section. And now this is a new game. This is what I just thought of this morning, and I have already implemented in my finite element course. And so this is an ongoing effort so that the students in the class follow what topics I have already gone through, and this is work in progress. Okay, and it's not just my work. I propose this to be a collaboration between me and the students, and so all you need, the condition would be attend the lectures regularly, right, and have a Gmail account so that you can contribute to edit this presentation file. And I have identified 2 students. You can just click here and then they will be full screen. And there are 2 students who I notice attend regularly and have Gmail account. And so all I need would be to give them permission to edit, and that would be Kyle and Matt. Kyle of team 6 and Matt of team 8, if you agree to participate. And so here is what I suggest. Those who want to participate, you can write the summary directly at the end of class, directly on the presentation, while the other teammates would write on the lecture summary. Of course, you also want to sign. So let me just put in Kyle, just as an example, okay? And I will put Matt in later. So Kyle, mcdonald@gmail.com. Okay, and so all I need is just to add Kyle, to give Kyle edit permission to this presentation. So Kyle should receive an email from Google, and that's it. And so if I click at share here, and Kyle's name would already be listed there as one of the author. Okay. So this is, like I said, an ongoing. I'll add Matt later on, and any other student who would like to participate. Ideally, I would like to have 1 student per team. Right? You can contribute to edit, and here I just do quickly just before I come to class, so it's not anything near complete. So from week 1 to week 4, I just brush out this, and like I said, it is ongoing. So we still need to do a lot of work, but eventually, as time goes by, you'll see that there's a vast amount of topics that we have covered, and so week 5 is starting here, so we can add more. Okay, so that's and F11 to get out of the full screen. So that's this topics covered, and that would begin from today. And now, as I mentioned here, I always, for example, the last meeting was meeting 14, and I always add annotation to what I wrote in class, and that's, I think, is a treasure that would help all students to clarify your notes. And I often recall at the beginning of the following lecture, right, to create a continuity. So you see that there's a lot of annotation that I added compared to what I wrote in class last time, right? So this is really something that you should really use to help deepen your learning. And sometimes you cannot take as much notes as I have written here. Okay, so I'd like to go back to section 53D just a little to remind you of, refresh your mind of what we did. Okay, we already, let's see, oh, not finite element, IEA 53D. Right. So we went through this part, actually this very first page here, we went through all of these, and this is the determinant of k minus beta m, and we obtain the solution, right? This is called also the characteristic equation here. Beta square minus 13 beta plus 36 coming from the determinant of this 2 by 2 matrix, okay? And with that, I'd like to come back to my notes here, and in particular what you see, or maybe even before this one. Yeah, so that would be meeting 13. So let me bring up meeting 13. Right, so this one. You see, in Wolfram alpha, I told you that we have done this part, we have done the determinant. I have explained completely diagonalization with different symbols and different arrangement for the second eigenvector. You know, I had the minus sign in the second coefficient instead of the first, but basically the same, right? So we have seen these, all of these, and we also, I have also derived the inverse. So what is left, as I mentioned, would be the characteristic polynomials, the eigenvalues, and the eigenvectors, right? I have shown you this. And so now you just saw the characteristic polynomial. I just said that the equation, okay, I'm looking for my notes, yeah, right here. This equation here, which came from setting the determinant of k minus beta m to 0, is called the characteristic equation. Okay, so now let me go back to this simple example, or in meeting 13. Okay, this example here, and show to you how you would obtain the characteristic equation, right? And that is basically solving the standard eigenvalue problem for this matrix K here. And so let's do that quickly. Okay, and this is also in the guise of reviewing, you know, what you saw with the generalized eigenvalue problem. Right, so you have 2 minus 1 minus 1, 2. And what is the standard eigenvalue problem? The standard eigenvalue problem, recall, is when, you know, the van should know, right? What was the standard eigenvalue problem? So we get the van with more active learning credits because he wanted to contribute several times. Go ahead, the van, what?
It should be k lambda.
Yeah, so compared to the standard, compared to the generalized eigenvalue problem, the standard eigenvalue problem would be?
Oh, it's equal to the identity matrix.
Yeah, when the mass is identity, so you only need to write like this, okay? And using exactly the same concept that you learned before, you can pull the right-hand side to the left and write k minus lambda I right? I is identity matrix, and multiplied by phi equal to 0, 0 matrix. Okay, we have seen all of this. This is exactly the same as the case of the generalized eigenvalue problem, except now that the mass matrix is replaced by the identity matrix. Okay, so we don't need to go back over again. So now what's the next step? What's the next step to solve this? How many unknowns here? How many unknowns in this equation, in this matrix equation? Active learning credit. How many unknowns? This is the same as what we went through in the last lecture. How many unknowns do you have in that, in this matrix equation? The one again?
3.
3, yes. The eigenvalue and 2 coefficients in the eigenvector. 3 unknowns. How many equations? Somebody else? We have gone through this. How many equations in this matrix equation? And 2, yes. So exactly the same as the case of standard eigenvalue problem last time. Sunderland and Anderson is team 7. Okay, so how do we solve this? Next step. You say that so that the eigenvector is non-trivial, you want the determinant of the matrix to be equal to 0. Okay, so I move forward. So you want, so for phi non-trivial, one determinant of k minus lambda I equal to 0. Okay. Right. So now it's just a matter of computing the determinant of k minus lambda I. So what is k minus lambda I? That's 2 minus lambda minus 1 minus 1, 2 minus lambda. Anyone having problem with this one? Okay, so so therefore the determinant, and again, if you have problems, please let me know. Don't let anything go by without asking questions. You get active learning credits. Okay, so what's the determinant? That would be 2 minus lambda square minus 1 square, right? So we're talking about 4 minus 4 lambda, right? Plus lambda square minus 1. So that's lambda square minus 4 lambda, right? And plus 3. Okay. And set this equal to 0. This is called the characteristic equation. I now remember that I can time is better. Okay, let's compare. Compare with this one. Right? Characteristic equation. Just a different variable name, but it's lambda square minus 4 lambda plus 3. Okay, that's how you get the characteristic equation. Check mark. We're done with this one. Okay, the question mark now becomes a check mark. All right, and so now the next question mark would be the eigenvalues. The eigenvalues would be the roots of the characteristic equation, right? And you can so let me write down here. Of the characteristic equation, and this characteristic equation here can be written as you can verify, you can solve, this is quadratic equation, you can find the discriminant and then you have the formula to find the roots, right? You can also verify that this is lambda minus 1 times lambda minus 3. Okay. And this is equal to 0, so therefore lambda is lambda 1 equal to 1 and lambda 2 equal to 3. Okay? Or you can quickly recall that if you have a general quadratic equation, a plus b lambda plus c equal to 0, then the discriminant is b squared minus 4ac, right? And lambda 1, 2, meaning the two roots together would be minus b plus or minus the square root of the discriminant divided by 2a. And if you do the calculation, you should get the same result. Okay?
Neither can the lambda values ever use I.
I'm sorry?
For instance, so in that square root, if that's a negative value, is that a possible in the is that in the domain of lambda to have the unreal numbers?
You mean so the question that Kai asked is whether it's possible to have negative eigenvalues? Is it your question?
Not only negative, but say like 3i, for instance, if the square root was
You
negative.
mean imaginary?
Yes, thank you.
Yes. In general, so this is, I asked you to review the single degree of freedom system, right? In my extra lectures. Remember that? Okay, so let me note this down. This is a review here. So single degree of freedom system. Right? What would be the equation of motion? Let's recall that the equation of motion is m y double prime plus c y prime plus k y equal to r of t, right? And if you look at the undamped, the free vibration, damped but free vibration. Free vibration means that no excitation. Okay, that's what it means. So it means that R is equal to 0. You are not exciting the system, and therefore your system, the equation of motion, is simply with 0 on the right hand side, right? And recall that what would be the trial solution for the homogeneous equation? We have gone through this. I mean, you should have gone through this in the review. Contribution. What would be the trial solution? I think we also did that before. We did review that.
Would be constant times e to the
lambda
x, or
e to the lambda t. If you use t as the independent variable, so mat of team 8 and chi of team 6. And this is also, is KZ here? KZ team 2? Okay, KZ team 2, sorry. Thought there was, because I did note down this question from KZ, and that because Mark asked this, KZ team 2, right? Is it KZ? Okay. So KZ, when I lecture on meeting 12, so let me bring up meeting 12. So I told you, this is a treasure. My handwritten notes with annotation after class is a treasure for you to study, because I fill out and reorganize. When I lecture on this part here, KZ asked whether alpha could be a general complex number. A general complex number means that a complex number that has a real part. This is a purely imaginary number, right? It has zero real part. Now, in this example here, which has to do with undamped free vibration. Undamped free vibration. The alpha is purely imaginary. You don't have damping. Okay, so the real part is zero. But in the answer that I'm about to answer to Kyle, in this case, when you have damping, yes, the root can have non-zero real part. In fact, will have non-zero real part. Okay, so the trial solution would look like this: y of t, let's say, equal to e to the lambda t. Okay, so the characteristic equation, and without going through this, because suppose that you should have reviewed from my extra lectures, you would have m lambda square. What's the next term? Active learning credit. Quick. What's the next term? The first term, I help you here. The first term is just m times lambda square, and the square comes from taking two derivatives of e to the lambda. Let me
Would it be C lambda?
C lambda. What's your team number?
Team 7.
Team 7. And
Tony.
what name?
Tony.
Yeah, so that's good. Lambda, I'll get you next time. Tony is the second time, so I try to bring in new people. So next term is, so Brenda, you can prepare for the third term. So second term is C lambda, and what would be the third term, Lambda?
K.
Sorry?
Just K.
K, yes, that's right, equal to 0. And when you solve this characteristic equation, lambda would be a complex number with non-zero real part. Why? Because the non-zero real part will be negative, and that will give you the exponential with negative exponent. That basically will get the amplitude to decrease to 0 as time goes to infinity. Okay, that's the meaning. And then the imaginary part allows the oscillation. Now, but let me take back. Actually, when you solve this characteristic equation, actually there are three cases. Case 1 correspond to real distinct root, and that is a non-oscillatory. And if the roots are negative, you just have the motion just go like this without oscillation, and it's called the overdamped case. When the root is double, the double real root, you have the critically damped case. That's the demarcation or the limit or the boundary between the overdamped case and the underdamped case. Underdamped case is when the discriminant is negative. Okay, so let me quickly write here. You compute the discriminant. Okay, discriminant delta. Okay, and so I don't want to get deeper into this because it's supposed to be discriminant delta. And if there are three cases, delta greater than 0, that's the overdamped case. Delta equal to 0 is the critically damped case, and delta less than 0 is the underdamped case. Okay, so in this underdamped case, that's what I call in my notes case 3, is when you have a negative real part and the imaginary part. All right. Okay. And so Did I answer your question, Kai? Okay, excellent. So, this is a review, and I really don't want to spend more time on that, but I will answer any questions. All right, so we already solved for the eigenvalues, right? So this is also a check mark here. And note that I have reversed the order of the eigenvalues. I call lambda 1 equal to 1 and lambda 2 equal to 3 for the reason that in vibration, the lower eigenvalues correspond to the lower frequency, the lower vibrational frequency, and that's also the most important vibrational mode, the fundamental vibrational mode. Okay. So now what we have left would be the eigenvectors, right? So how do you find the eigenvectors? So here, so you already have the eigenvalues, right? And now the eigenvalue problems can be written as follows: Phi1 equal to lambda 1, Phi1. And lambda 1 is now known, right? Lambda 1, you know that it's equal to 1, right? We have found lambda 1. And you can also write, just like before, K minus lambda 1 I times Phi1 equal to 0 matrix, right, with the underbar. How many unknowns? Active learning credit, quickly. How many unknowns here? Two. How many equations? How many? Who said 2? Who said 2?
7.
I'm sorry. Somebody said 2. The man said 2? Yeah. So let's pick. How many equations, Robert? 2 equations. Okay. 2 unknowns, 2 equations. So, but we have a problem. We have a problem. And Robert is team 3. Or team 5, yes. And next time I'll pick you. So be prepared for the next question. Maybe you wanted to say something. What is our problem here? If we have two unknowns, 2 equations, what's the problem here? Can you solve this system? What was the determinant? What is the determinant of K minus lambda 1I? We just did it. What was the determinant? 0, right? Because that's how we found lambda 1. Because if the determinant of K minus lambda 1I was not 0, then Phi1 is 0. Trivial. We don't want trivial solution. We want non-trivial solution. Okay? So, so we want the determinant to be 0, and let's write down the result. Okay? So you can write the following: the matrix K minus lambda 1I is 2 minus 1 minus 1 minus 1 2 minus 1, right? Because lambda 1 is equal to 1, okay? And times Phi1 1 and Phi1 2. These are the 2 coefficients of the eigenvector Phi1, and this is equal to 0, 0, okay? Now, so this matrix is simple. This is just 1 minus 1 minus 1, 1, okay? Now, you know that, I have shown to you that if Phi1 is eigenvector, then Phi1 hat equal to epsilon Phi1 is also an eigenvector. We have done this before. What it means is that if phi1 is an eigenvector, then multiplying phi1 by any scalar, you can still get an eigenvector because phi1 and phi1 bar are collinear, pointing into the same direction or parallel. Okay? So you can think of let. Okay, you can think of the following. This relation here, maybe I can use this matrix here. Okay. And think of putting the hat up here, because phi hat is also an eigenvector, and you can let select phi1 hat to be equal to 1, right? And that's equal to epsilon phi1. Okay? And so therefore epsilon is equal to 1 over phi1, right? And so therefore phi 1, 2 hat would be equal to what? Epsilon phi1, 2, and so therefore equal to phi1, 2 divided by phi1. Okay. So what it means is the following. This set of equation here can now be written as follows. Let me go to the next page, and I can zoom out so you can see the big picture. Maybe I can squeeze it in here. And now I replace phi1 hat by 1. Okay, so that I have only one unknown. Now, with this one unknown phi1, 2 hat, you can select either equations, right? Because you have two equations, one unknown. So let's say select the first equation. So let's say first equation, and that would be 1 minus phi1, 2 hat equal to 0. So therefore phi1, 2 hat is equal to 1, right? So what it means is that the first eigenvector phi1 hat is 1, 1. Okay, that's the eigenvector that we need. That's the first eigenvector. And say if you select the second equation, you get the same result. Okay, from the second equation, minus 1 plus phi1, 2 hat equal to 0, and you still get the same result. So either equation would be fine. So we found the first eigenvector. Now for the second eigenvector, you follow exactly the same procedure. You take k, yeah, so I just copy from here. You just take k minus lambda 2, right? So replace the index 1 by 2. Okay, so remember that lambda 2 is equal to 3, right? That's what we found from solving the characteristic equation. So k minus lambda 2 would be 2 minus 3 minus 1 minus 1 2 minus 3, and then over here you have phi 2 1 phi 2 2 equal to 0 0. Okay. Now this matrix here is minus 1 minus 1 minus 1 minus 1. And now you know the method, right? The method is just set the first equation to 1 and find the second equation. So set the first equation to 1. The second equation would be the unknown. Whether you have the head on or not doesn't matter, because remember you can multiply the eigenvector by any constants and it's still the eigenvector. Okay, so and that's it. Now pick any one of the two equations to solve for phi 2 2. So say pick out the first equation. So the first equation would give you minus 1, right, and minus phi 2 2 equal to 0. So therefore phi 2 2 is equal to minus 1. So therefore the second eigenvector had been found. That's 1 and minus 1. That's it, right? So now we have found two eigenvectors that we had to accept. Let me zoom out. We have found two eigenvectors, this one and this one. You know, later on this one you can rename as phi 1, right? Because if phi hat differs by phi 1, phi hat differs from phi 1 only by a scalar. So if you choose the scalar to be 1, then phi hat is the same as phi. Okay, so these are the two eigenvectors that we had accepted at the beginning, and therefore we can now honestly put a check mark here. Okay, critical thinking question. You look at this matrix S. You see, this is like the matrix of the eigenvectors, and so you see, you know, the way Wolfram alpha organized is a little messy, not nice. You know, they call lambda 1 3, lambda 2 1, but when they get to the diagonal matrix, they order lambda 2 first and lambda 1 after. You see, so in the way that we do in my notes, it's better. I call lambda 1 equal to 1 and lambda 2 equal to 3, and so the order of my diagonal coefficients here would be, you know, the smaller eigenvalue and the bigger eigenvalue. So, but you see, if you look at lambda 1 equal to 3, okay, lambda 1 equal to 3, and v1 is equal to minus 1 and 1, right? But because they put lambda 1 in the 2 2 position here, that's why this column here, minus 1 1, is in the second column. Okay, and likewise the lambda 2 is put in the 1 1 position, so therefore the second eigenvector would be placed in the first column of the matrix S. The matrix S is the matrix of the eigenvectors. It's equivalent to the gap phi in my notation. Critical thinking question. You see the eigenvector here, minus 1 1. How do you, what's the argument to bring this minus 1 1 to the eigenvector that we found? You know, 1 minus 1. You see, what I'm asking you is the following. Yeah, let me zoom out here. What I am asking you is to connect. What would be the reasoning to connect this second column here, or to change this second column in such a way that you get the second eigenvector to be 1 minus 1 with a minus in the second coefficient based on what you had learned in this lecture and in previous lecture. We just review the value.
Didn't we just say we can multiply phi by any constant?
Yes, you can multiply any eigenvector by any scalar, but it's still an eigenvector, right? What would be that scalar? Someone new wanted to contribute here. Then you raise your hand, so now this is an opportunity.
-1.
What? Raise your
Negative-
hand so I see. Yeah, so
negative
multiply by -1. Yeah. So if you either you can start from here, you multiply by -1, you get that one. If you start from that one, you multiply by -1, you get this one. And both are eigenvectors, okay? Because they are just differ by a scalar. What is your team number?
5.
Team 5. And name?
Thomas.
Thomas.
Yes.
Second time, yeah. Very good. So that's it. So now I have completely explained everything. Everything in this Wolfram Alpha page. They are not useless information. Okay, whatever is in that Wolfram Alpha page, the properties of the matrix are very useful, very important information or properties that you can use to do further work, particularly uncoupling the system. All right. So now with that, I have show you how to use what you learned from the generalized eigenvalue problem and apply to solve standard eigenvalue problem. And therefore, the report problem should be simple, right? Easy, exactly using the same method. So now we can move forward on this part. Eigenvectors, yeah. This is now very similar to what I just discussed with the standard eigenvalue problem, but now the mass matrix is no longer diagonal, right? It's no longer identity. It's diagonal but not identity. Okay, so let me walk you through gradually. So this is the generalized eigenvalue problem, k phi equal to beta m phi. By this time, we have already solved for the eigenvalues. So now what we are looking for would be the eigenvectors. Okay, we solve the eigenvectors now. Two unknowns, two equations. Okay, two unknowns, two equations. Beta is supposed to be known now. So let's move on. So here is the same thing. Essentially, what I wrote down here. Okay, what I wrote down here is that we already have two eigenvalues, so that the generalized eigenvalue problem can be written with an index I, right? I equal to 1 or 2, and phi I is the eigenvector corresponding to beta I, right? So for example, I is 1, beta 1. What was beta 1? Beta 1 was equal to 4, and beta 2 was equal to 9. Okay. So so phi 1, the eigenvector would have two coefficients, right? Phi 1 1 and phi 1 2. Exactly the same notation as for the standard eigenvalue problem, with the exception now that the mass matrix is not identity. That's all. Okay, and the method is identical. And so therefore, the next step is to find the first eigenvector corresponding to the eigenvalue beta 1, because beta 1 is already known. Okay? Beta 1 was equal to 4, and now we have two unknowns, which are the two coefficients of phi 1. And now you can rewrite the generalized eigenvalue problem in that form, and so this is the fully expanded fully expanded form. Thank you, Casey. Now I know your name. And so this is fully expanded, meaning that where I had replaced beta 1 by 4, right? Beta 1 is equal to 4. 2 here came from the mass, right? This is mass M1 and mass M2 is 1/2, and this is beta 1. The other coefficients are the coefficients for K. And that's it. It looks very similar to the standard eigenvalue problem, and then you get this part, and the next step would be to set phi11 equal to 1 and solve for the other coefficients. Okay? So we'll continue next time for the details. So now you can collaborate and write a lecture summary, and if Kyle has a computer, you can immediately collaborate to write the summary online. So I can work directly here. Let's say week 5. We just need
I think since the last 2 problems, I'll take the second last year.
Yeah, that'd be fine. I can get started with the same problem.
yeah, because you can be fair.
When it's raining, it's definitely starting.
Last time it was so that we could edit one document. I'll check out both on my background. I think like they're on some of the
Gary's on 4.4 and 4.1 600. I know it's like, I'm one thing below 470. Yeah. Not really. I mean, it's about 2.5 miles.
Yeah, no.
4 miles.
That way you can go.
And then there's 34.
Yeah, I know I gotta get. That allows you to take care of little things.
Okay, yeah.
If I get everything to the dock, yeah.
No, utilities are usually another like $50.
Yeah, it's pretty easy stuff with all the base work done. You just gotta like,
Yeah.
Okay, so feel free to add in event. For example,